In this video, we will look at some techniques that do not have an explicit name but are very useful in solving Codeforces problems, especially the ones that involve bit manipulation and operations that have something to do with a subarray. So you must already know this trick known as the difference array trick, but in this video, I will show you how you can convert this trick and apply it to the world of binary strings. So the problem statement says that you are given a binary string. So the array that you see on the screen, this is a binary string, and some entries would be 0, some would be 1. And in this binary strings, you are given some bulbs at certain location. So for example, this is a bulb at location 0, at whatever location. This is a bulb. So all the bulbs, they have the value set to 0. So their bit is unset. So these are some bulbs located. So let me color all of these bulbs in yellow so that you remember that. These are the bulbs that are given to you. Now, in one operation, you are allowed to select any range L to R given that it contains at least one bulb. That is, it should contain at least one yellow element. So suppose you select this particular range from here to here. It can contain more than one bulb, that is fine. And remember that this is a binary array. So everything else, all the bulbs are for sure set to 0, but everything else could either be 1, could either be 0. So you can select this L to R provided that it contains at least one bulb, and then you can flip all the elements in it. Like you can set 0 to 1, and if this element is already set to 1, you can now set it to 0. Now you can see that all the bulbs have the initial value of 0, and your goal is to make the final array 0 0 0 0 0. Like you have to make a string of zeros by performing this operation. Like in one operation you can select any subarray and flip their bits. So you have to perform this operation the minimum number of times, and the problem statement asks you to find out what is the minimum number of moves to make all the bits 0. Now this might sound like a very complicated problem at first. So let's try to tackle it step by step. So let's start out with the first operation, and notice that the operation says that you are allowed to do something on a particular range. And in one of my previous brain gym videos, I talked about a case wherein, especially the ones that involve binary strings, right, where you have to deal with 0 1s etc. So the name of the video was substring of substrings with equal count of zeros and ones. So in that video I showed you a trick of prefix sum, and what this prefix sum used to do was convert our reasoning from subarrays to just two elements, because it is very difficult to think about so many elements at the same time. This is L and this is R. So you have to remember that you are doing the operation on each element every time. So is there a trick that we can use so that we don't have to worry about subarrays and we can instead focus on some elements instead? Yes, if you are coming from the number theory world, you might know that if you have this array and I ask you to repeatedly perform these queries, I will give you an L to R and you have to add some delta to it. And this array is static. That is, I will just give you a lot of L to R queries. Like I'll give you L2, R2, and then you have to add delta 2. And then L3, R3, and then you have to add delta 3. So how do you solve this problem? Because you cannot afford to iterate over each of the element and then take off and time to update the deltas. So you solve this problem by realizing that if you are adding something in each element of the range, what is the one thing that can remain invariant? So the invariant is if both of them gets increased by delta, their difference actually does not change. So that's why it gives us a hint that for this problem, we should, instead of maintaining the array, we should now maintain a difference array. So we should now maintain a difference array. So with this difference array, you can see that adding a delta between L to R, and so the difference array would be simply D of I is equal to A of I minus A of I minus 1. This is the difference array. Now you can see that in a difference array indicates what is the difference between these two elements. So when you do some range on L to R, the difference between anything that is inside the subarray, they do not change. The only difference that change is the boundary point. So this border and this border. So you will have to do difference of L. This will increase by delta, and difference of R plus 1, this will decrease by delta. And this is how you can process all the queries, and at the end you can convert this difference array to a prefix sum array, and then you can retrieve your original array. So this is a very fancy, very cool trick to handle range updates that do not involve querying the array elements during these operations. It can only give you the entire array once all the queries have finished. Now, how do we bring over this concept to the bit manipulation world? So now, if you have this array and I ask you to flip, if I ask you to flip certain bits of the range L to R, so this is L and this is R. Then notice that what is the thing that you can maintain as invariant? So if this, first of all, let's see what does flipping a bit mean. So 1 transforms to 0, but 0 transforms to 1. So can you write it down in a fancy mathematical way? So if you are new to bit manipulation, that might be new to you, but it is actually a very well-known fact that flipping a bit, there is a fancy way to write flipping a bit, that is XOR 1. And you can see why this is true. Maybe you cannot come up with this by yourself, but you can at least see why this is true, because 1 or 1 is equal to 0 got flipped. 0 or 1 is equal to 0, so 0 got flipped. So this means that you are flipping the entire range means applying the XOR 1 to the entire range. This means that in the XOR world, XOR itself is the addition, XOR itself is the subtraction. So we can just maintain the difference array. And what is the difference array? Like I said, XOR is the addition, XOR is the subtraction in its world. So this is like the God. So you can, if you just maintain the difference array or the equivalent of difference array, whatever you want to call it, like what should you call it? Okay, whatever you want to call it, like but the formula would be like each element ai, this element will contain the XOR between these two. So you will have something like difference of I is equal to ai XOR a of I minus 1. Now you can see that why this will remain invariant for any element that is inside the subarray range that you have selected, because you are XORing 1 over here and you are also XORing 1 over here, and 1 or 1 cancels out. So that is why only the boundary points would change. So the boundary points will get flipped and nothing else. So this will get flipped and this will get flipped. So now you can see that we are already making some progress. We started out with a problem that dealt with subarrays, and now we are down to a problem that only involves selecting two elements and then flipping them. So some progress so far. Now how do we make further progress? Because the problem statement said that there are additional rules, like there were some bulbs and then you could only select the range that involved the bulbs. So let's try to analyze that and see what happens. So if this is your original array with the bulbs that are there, and you know that you can only select a range if you have a bulb present at inside that range, at least one bulb should be present inside that range. Then when you convert this to a difference array, and by difference array I mean difference array in the world of XORs. Okay, so in that configuration you will realize that the position of the bulbs will not change. The bulbs will still stay at this position because they are fixed. So these bulbs are there at this position. And after that, let's transform the entire problem to this prefix, to this XOR array, to this XOR different XOR array. Let's call it like that. Or okay, XOR diff array, whatever. So our goal was to make the entire array as 0 0 0 0 0. So what is the XOR diff array of this? That is also 0 0 0 0 0. So this means that all the set bits that are present in this XOR diff array, we have to turn it off to 0 as soon as possible, and by respecting the rules that are given in the problem statement. Now you know that you have to turn off all the set bits. Okay, so first of all, assume that the bulbs were not there, and you are allowed to select any subarray range and then turn it off, flip the bits. So what would the answer be in that case? So in that case you will notice that once you have gotten the XOR diff array, this is the XOR diff array, then you would have had some ones at some location, like there would be a 1 here, there would be a 1 here, there would be a 1 here, 1 here, 1 here, 1 here, and 1 here. Now how do you compute the minimum number of operations to convert this XOR diff array to a array of 0 0 0? How do you do that? So you can realize that in one operation you can select two entries and then you can flip them in this XOR diff array. So you will select these two and you will flip them. Then you will select these two and then you can flip them. Then you will select these two and you can flip them, and then you can select this and you can flip it. A single element can be selected in the XOR diff array. Why? Because this corresponds to a subarray with just one single element. So that is the valid case. So this means that the answer, if there were no light bulbs present, would have been simply frequency by 2 upper bound. So it should be what should I say, like, so if it is 5 by 2 then it should be 3. Okay, now with the bulbs that are added, you know that you cannot randomly select these subarrays and then do your operation, because what if the bulb is present over here, right? Like what if the bulb is present over here, right? Or what if the bulb is present over here? In that case, selecting this subarray and then flipping it is not a valid scenario. So what do you do in that case? Can you come up with a strategy to solve it? So to solve that, we'll be introducing another idea. So let's label the position of the bulbs. So suppose the first bulb is present at this location. This is the first bulb. Okay. So this means that there will be some elements to the left of it. and then assume that the second bulb is present over here. Then there would be some element to the left of it, and then third bulb is present over here, and there are some elements to the left of it. Now what can you see? So if there is an element 1 over here and 1 over here, so your goal is to turn off both of these ones to 0. But you will see that since the first bulb is here, then you cannot pair up these two elements because there is no bulb in between them. This means that all of the ones that are present on the left hand side, they fall into the same class, or should I say same color. So there are some ones in this segment that will be of the same color, and when you are turning off 2 bits, you cannot pick elements of the same color because there is no bulb in between. And then there will be some bulbs here. So there is a bulb here, and then there will be some ones over here. So you can clearly see that you cannot combine these two ones to turn them off. Why? Because there is no bulb in between them. So that is why we have colored all the bulbs, colored all the ones in this segment with red color. Then there will be some ones in this segment. So let's color them as green. So there is one over here, one over here, one over here, one over here. By the way, all the gaps in between, they are zeros. So that is why I am not writing them. So don't think that there is no gaps in between them. There are gaps in between them, but they are zero. But so we don't care about the zeros. So now you can already see that with each bulb, you can color all the elements that are in between two bulbs of this with the same color, because they should never be paired with one another because there is no bulb in between them. So now your problem becomes, suppose there are n such colors. So your problem is given n elements, the problem would be given n colors, and there are ai elements of each color. Okay, so there are, like, let's say 5 elements of color blue, and then there are 4 elements of color red, and then there are 4 elements of color green. So this is green, this is red, and this is blue. Your problem is that you are allowed to do pairing, but the pairing should not be between same color. So pairing should not be between same color. This means that the problem statement essentially boils down to, given A1, A2, A3 up to AN, these many balls of color C1, C2, C3 up to Cn, you have to put them into boxes, and each box can contain a maximum of 2 balls. It can contain 1 ball, and 1 ball indicates that you are taking the entire prefix, right? So it will have this, one box can contain maximum of 2 balls, and any box can contain max 2 balls, and each box should not contain balls of the same color. Should not contain balls of same color. So we are just looking to solve this problem. Now this exact problem has appeared in a recent Codeforces round, and I have already made a video on it. So this is a very tricky problem, but it is one of those problems where once you see the solution, you will never forget. And the name of this video is this one. So you can check it out on my channel. I will also link it in the comment section. The ChatGPT can't solve this puzzle. So this exact problem has appeared before, and this is a very known algorithm. So that is why I wanted to create another video on it, so that everyone knows about this technique. So everyone knows, maybe not you, but everyone knows that the answer to this problem is basically max of uh, summation of ai by 2, because worst case you will have worst case you will if there are total s elements, one second. So if there are total of s element, then of course you will need s by 2 boxes, because one box can accommodate only 2 elements, or the max frequency. This is the necessary as well as the sufficient condition. Now I'll not go deep into why this is true. If you want to learn it, you can watch this video. It has the proof for this. It has a very elegant proof for this. But in case you are still in doubt, I will quickly share the strategy that always works. And the strategy that works is, consider the highest frequency element and call it. So consider the highest frequency. So assume that is x. So definitely you will need x boxes, that is for sure. So because like if the highest colored frequency is x, like if there are 23 balls of blue colors, then you will need 23 boxes, because you cannot pair two blues in the same box. So you will need x boxes, that is for sure. So you have x, sorry, you will have like, let's say you will have a blue ball over here, one blue ball, one blue ball, one blue ball, up to 23 times. Okay, you will create 23 boxes. Then the remaining is what? If the remaining sum is s, then the remaining part is s minus x. So if s minus x, that is the remaining total, is less than or equal to x, then you will see that 2x is greater than or equal to s, means x is greater than or equal to x by 2. It means that if the maximum frequency is greater than half the count, and this is the idea where the frequency and the total sum comes into play, because a lot of people get confused, like how come this problem immediately jumps to frequency and total sum. So you can see how, because you are allocating one box for each of the balls of the same color with the highest frequency, and then what you can do is, and that is the optimal strategy, for the remaining balls you start rotating them in a cyclic fashion. So you add one ball over here, whatever the color may be, one ball over here, 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 and so on. And you can see that in this manner you will run out of balls before you try to add the third ball over here. And why would you do so? Because x frequency is greater than the entire set of elements combined. So this is the optimal strategy. So now that we know that we have created some set of colors for each of the set bits, then we know how many total. So we can simply count how many balls of each colors there are, and then compute the answer to this problem as max of frequency of max color comma total by 2. So this would be the ceiling, not floor. And this is how you can solve this entire problem. So you see, we introduced two important techniques. One is that doing some operations on a range most likely can be converted to doing operations on just two elements via this XOR diff array, or whatever you want to call it. That is the one trick that we learned. And the second trick is that whenever you are posed with the problem of filling, whenever you are posed with the problem of filling balls in boxes such that one box should not contain two balls of the same color, then the optimal strategy is to fill the maximal frequency first and then rotate the remaining balls, and you will run out of balls before you add a third entry in any of the box. So this was the solution. The overall code would be pretty simple. As you can see, you just have to convert it to a Zordif array, count the number of ones between each bulb segment, and then treat those as the number of balls for a certain color that you have. So yeah, this was a unique and creative way to approach this problem. And let me know if you were able to solve it in the Codeforces round. And if you have any feedback, let me know in the comments. Thank you.